My name is Myoungwon. I'm a software engineer at Samsung Electronics. I'm here to talk about TiDedup, a new distributed deduplication architecture for Ceph. First of all, thank you for taking your time out of the busy schedule. I'll start with explain background of where our work is originated. Before we go any further, I'd like to explain the background of conventional deduplication system. Deduplication is a well-known technique that for data reduction. It eliminates excessive copies of data. In dedup system, as shown in this figure, the input data denoted by an object is divided into several chunks using fingerprint algorithm. The system then generates the fingerprint value from the data. After that, the system looks for final location where the chunk is located using fingerprint index. This fingerprint index has an important role because it can help the system fast lookup. Anyway, using fingerprint index, the system finally get or store the chunks at the physical address. So, how can we implement such deduplication system on distributed storage system like Ceph? This was our prior work. Ceph community discussed these topics about 5 years ago. At that time, most of the developers concerned how such deduplication logics work with Ceph at scale. Because I explained in previous slide, deduplication needs the fingerprint index for fast lookup. So if we bring in such index into Ceph, it might hurt Ceph's philosophy, shared nothing architecture, because it is centralized. So we had proposed the double-hashing techniques before. This idea is the fundamental idea of TiDedup, so I'm going to explain this briefly first. Let's assume deduplication is done. Users submit their IOs as usual with the OID and data. Then the submit request is bound for the specific server node using fingerprint algorithm, using hash algorithm called Crush. Then Ceph generated the fingerprint value from the data. Using fingerprint as OID, the data is relocated from the base tier to chunk tier, as shown in this slide. As you can see, during this relocation, the hash algorithm called Crush is used twice, so that's why we call this double hashing. Anyway, as a result, we were able to completely remove the fingerprint and exit Ceph, so we don't need to consider it anymore. Let's clarify, to clarify the terms, I will call the metadata objects, the objects, and the objects on the chunk tier will be called chunk object. But this idea is not good enough to make Ceph's deduplication usable. When we test it and did integration tests with other features, we found several problems we missed. The first thing is that performing deduplication might not be helpful in terms of storage saving. Ceph is kind of a general purpose storage system which provides block, file, and objects. So even data center operators cannot expect which types of data, which types of workload is stored in their storage cluster. If the backup workload is dominant in their storage cluster, it would be beneficial to performing deduplication without question, but that's not true in their environments. So this motivated us to think about the more flexible way. Second limitation is we have experienced is structural limitation. The prior approach has a tiering structure that background thread performing deduplication jobs such as enumeration, chunking, and moving chunks, but it significantly disturbs foreground IOs as the number of objects is growing. This is because it holds object group level locks for a long time to protect system consistency. On top of that, Ceph only provides fixed size chunking algorithm. This algorithm is not always good best way for data reduction because of boundary shift problem. Third motivation is snapshot and scrub time. Ceph transparently provides object level snapshot and to maximize deduplication effect, deduplication on snapshot objects is needed. But the fundamental problem is that adding chunk reference, which needs to be distributed across the cluster, must be done to complete snapshot creation. So, as you can see, snapshot must be delayed until all operation is done. As the number of chunks the object has is growing. Another problem is scrub. Scrub is kind of reference garbage collection that periodically checks the chunk is valid. In prior work, the reference leak can rarely occur because it adds chunk reference synchronously, but it does not check completion of chunk deletion. This is based on first position of design. The thing is that time to increase, the thing is that the scrub time to complete the increase exponentially as the number of metadata objects grows. So in this example, to check if chunk object A's reference is valid, we need a pull search, which means only three messages must be sent to the corresponding metadata objects in this example. Moving on to the next topic, I will give you the design of TiDedup to explain how we address the problems I mentioned. The overall architecture is demonstrated in this slide with respecting to core principle called double hashing. TiDedup proposes three key designs. This slide explained what selective cluster level crawling. First, the crawler is introduced as a separate thread to perform a deduplication selectively. The role of a crawler is that it searches metadata objects on the base tier and then perform deduplication if the object has duplicate chunks more than threshold time. With efficiently run crawler with normal I/O, we two modes, incremental and pull, are also proposed. Incremental modes gradually make a progress to save computing resource, but in the other hand, pull mode search all dedupable chunks on the base tier within an iteration. The crawler also controls object states and its measurements. Object state should be one of dedup, hot or cold. The crawler is basically stateless to overcome any practical issues via simple execution. The crawler only maintains the fingerprint store to check dedupable chunks. This store is refreshed whenever the search is done and initialized every execution time. Second is event-driven architecture. This architecture is designed to react on action in the event of external APIs without any background work with CDC, called context-defined chunking. To do that, TiDedup implements several APIs such as set chunk, tier flush, tier ebix. TiDedup also modifies original I/O paths such as read and write for this architecture. For example, on read, TiDedup looks for the corresponding chunk input T, which is newly added for deduplication, and then for this read request to the chunk objects, if chunk state is missing. If chunk state is clean, it directly returns the data to the user. On write request, TiDedup handles the write request in the same way as normal IOs, but it only clears the chunk input T because the chunk boundary is meaningless. Please keep in mind, chunk boundary needs to be recalculated because the chunk state is mutated based on content-defined chunking. There is a representative API called set chunk in this architecture. Set chunk is introduced to set a part of object to dedup. All operations in set chunk are done, what that means that TiDedup would never update dedup metadata until all operation is done. So it is safe if the failure occurs. The third idea is wide shared reference. Using instead of using a number as a reference, TiDedup exploits Ceph4 wide format. Ceph4 wide format includes location information such as tier name, tier, and object's name. So as shown in this example, if we read chunk object A, TiDedup is able to know which metadata object must have a reference for chunk object A. So TiDedup needs only one additional read for chunk evaluation. With this back pointer, TiDedup implement OI shared reference. The goal of OI shared reference is to minimize the generated message during snapshot creation or deletion. When snapshot is created, TiDedup checks the prior and next chunks in the adjacent snapshot, marked as red circle, then does not generate any message if either prior or next chunk is identical. For example, the number of chunk triple A in this example is 1. Like chunk creation, chunk deletion does not generate any message if if adjacent chunk is identical. TiDedup only generates the deleted message if there is no same chunks in the adjacent snapshot. Test and evaluation. First experiment I will introduce is deduplication effects by TiDedup. We collect the factory data generated during our memory manufacture processing for 16 days. There are 4 types of workloads. We replay these captured data into our Ceph cluster using object service. As you can see, the result, workload 3 shows the highest deduplication ratio because it contains incremental, it contains archival files and logs, for example, time series logs. On the other hand, workload 4, which consists of methodology and inspection image files, is not affected by deduplication. Next experiment is throughput test. We did throughput test using YCSB to see performance degradation between TiDedup and the prior. As you can see, the figure, the fixed, which represent the prior work, suffers from performance degradation because of background work. On the other hand, TiDedup shows the constant performance in terms of both throughput and latency. Besides, we have done more experiments. Please see our paper if you are interested. This is the last slide of my presentation. So I'd like to summarize what I say. The prior work has a few limitations to be used in Ceph in production. So we proposed TiDedup with 3 key design. TiDedup shows the reasonable performance with data reduction. The source code is available at Ceph GitHub or our personal repository. And we welcome feedback. We believe users' feedback makes our TiDedup much stronger. So if you are interested, please give us your feedback via GitHub, Ceph's developer list, email, whatever. Thank you.